All right, so I guess today, for the first time, since I can't delay it any longer, we'll actually like do some PDE. Supposedly, it's a course about PDEs. All right, so just some quick recap. So what we've done, so we're discussing this characteristic initial value problem. Ultimately, we're interested in the Einstein vacuum equations. As a precursor to, and I stated for you the theorem that I want to understand for the vacuum equations, but of course, those are complicated, right? And so we start with some example, and I've been spending some time to do slightly less hand waving than usual going over that example. And we were interested in, we saw that the theorem, so we considered as a warm up to understand nonlinear wave equations, right? We saw that you cannot, the theorem is false for a general nonlinear wave equation. And then I gave, and we saw what the obstruction was, certain kinds of nonlinear terms. Then I gave an example of a nonlinear wave equation that should be good, and we want to prove the, the theorem for that. And then we showed that basically we saw that everything reduces to proving some estimates, basically. And you can even, you can assume that you have a nice solution and you just need to prove these estimates. And you can even sort of assume the estimates you want hold at a slightly worse boundary, you need to improve it, right? Okay. Now, so now before we get in, so the immediate goal will be to show that works. So now before I immediately jump into that, I want to go over the types of estimates that are going to go into that, right? Which are these things I mentioned. Again, just in case I know there's a wide variety of background of people following the course, and so in case you're not so experienced with hyperbolic PD, I'll go over what null energy estimates are, um, and we'll also see some. That'll be the main sort of new thing, and then also some transport equations, how you can use sort of transport estimates, maybe even in combination with energy estimates. And those will be the main like ingredients that will go into proving that making the last step of that bootstrap argument. Okay, so so this will be, so we're just gonna look at for now just sort of say inhomogeneous wave equation F for now. All right, and so and then we can write this, if you remember, as minus du dv of
And we're still in Minkowski space.
yeah, this will be Minkowski. Yeah, yeah, everything's Minkowski for now. This is all. Again, let me just look at my notes. I'm more likely to get my constants straight. Somewhere in here. Where are we? I can divide by, yeah, I'll divide by 4 at the end. All right, yeah. Yeah, so let's write it like this. Um, um, yeah, I guess I'm right. Plus, yeah, 1 over v minus u. Yeah, there was a 4. All right, dv like this. And then we get our, then there'll be, right, plus v minus u to the minus 2. Then there's this spherical Laplacian there. Right, and then this would equal these factors of 4 are not important, but okay. So now, all right. So let me first remind you of something that you will have seen and at some point, hopefully, in your mathematical life, which is a regular energy estimate. Right. So remember a regular energy estimate. Well, regular is a bit of a, could sometimes be a judgmental term, not to indicate that the other energy estimates are abnormal or something. But anyway, the first energy estimate you learn maybe is more accurate. Which is roughly the following, that you multiply equation with, well, because of the way with the signs here, you probably want to multiply it with minus dt of psi. Integrate over a space-time region and integrate, well, by parts. over some space-time region. Right. And and you get and some stuff happens, right? And so we know what stuff happens here. I won't write this estimate out because we know it. Is that well, basically you'll get an equality. Well, somehow you integrate over the space-time region. There are no all the terms integrate out. You get identity, which is known as like the conservation of energy. So for example, if you do it between two copies, R3 at some later time and R3 at some earlier time, you get like the gradient of the solution plus the integral of the time derivative squared is equal to the same thing at an earlier time. Okay, cool. Um, that's fine. That's the regular energy estimate. It turns out I'm not going to get into it because, well, just sort of for the sake of time. It's not really that important. There's a much more geometric way to think about energy estimates that doesn't involve, multiplying by random things or whatever. Um, but all I'll say here, though, is that you can generate something like an energy estimate. Now, the fact that the normal energy estimate produced like somehow there were like integrals on some space-like slice equal to some other integral on a space-like slice and nothing else. That the fact that there was nothing else, that there was no like space-time integral in that thing. Of course, I should say, well, when you multiply by dt and do all the stuff on the one side, of course, somehow this f will always be sitting there. You'll always have some space-time integral, right, of that. So there's always that. But sort of other, with d by dt exactly on Minkowski spaces where everything happens that all the other ones cancel. That's something that has to do with the fact that d by dt is a Killing vector field. Okay. Um, so if we forget about the requirement that there's no sort of space-time term, um, then we can think more flexibly about energy estimates. And in fact, there are useful identities of that sort can be accomplished by replacing multiplication by d by dt with any future causal vector field. And okay, and again, I won't go systematically into a discussion of that. Let's just see what that looks like. And that'll sort of be enough for now. And then there'll be something else. Well, I'll write that out. And then there's an extra thing you can do, which is you don't have to just multiply. Well, like I said, a vector is really a causal vector field. I mean, it doesn't have to be like a constant coordinate derivative. I can also multiply this by a function and do the same integration by parts. And all right, if you just do a random function, if you don't put any constraints on it, that won't be useful. But there are certain choices of functions which produce extra good terms in certain settings. Okay, and again, these are things that can be understood very geometrically. I'm going to just go over it in a very like uh, keeping my nose to the ground sort of perspective here, just like the mechanics of what happens. Okay, so what I'm going to do, so we're going to look at null energy estimates. All right, so what we're going to do here is we're going to multiply. So this will be the first version. We're going to multiply by minus dv of psi or minus du of psi. So let's just start with minus dv. So when we multiply, then I'm just going to write all these terms here. So let's just look at this term here. Of course, there's some volume form floating around. But anyway, somehow I'm not going to worry about things too much. All the integration by parts I'm going to do are going to be away from near r equals 0. So you don't have to worry. Don't have to worry about anything near r equals 0 for this discussion. I'm keeping things really at the simplest, most pedantic way possible. All right. So this term we can write as 1/2 of du, right, of dv squared, right? Okay, and then I also want to look at, so right now I'm going to just look at the terms that involve second derivatives in them, and I'm rewriting them as lower order terms and higher derivatives. All right, so then there's this term, and so when I multiply by minus d by dv, okay, and let's also go ahead and actually just integrate this over the standard sphere, right, then this is still true, right? Okay. Then we go over here. There's also this term that you could get. Remember, if I don't write a volume form, it's always the one that is kind of clear. So in this case, I'm integrating over the round sphere, so integrate with respect to the round metric. Okay, so this one I can write as I can integrate by parts on the sphere once, right? So I can write that as S2. Well, I can even pull out this v minus u. Get rid of the minus, so I get gradient S2. I guess I should be consistent. For some reason, I decided to put dots like that to denote it. So this is, okay, contracted with this gradient, right? Okay, the contraction is contracting with the metric on the sphere, spherical gradient, and then I can use the similar structure like that. So now I can pull this out everywhere. So I'll write this as d by dv now times integral. Wait, something. No, I guess that's okay. All right. And now just looking at, so now let's draw a region. Remember, we're going to be interested in these rectangles, these characteristic rectangles, right? That's where we're going to have to do estimates. So now you can imagine, so let's draw like one of them here. All right, and so if this is u equals u naught, oh wait, let's say v equals v naught, this is u equals say u naught, u equals u1, and v equals v1, I can take, so using these facts, I can multiply, I could take the equation, I multiply it by dv, and I can integrate by parts over this rectangle R. So I integrate, so I'm gonna, well, I'll write a double integral just to indicate that it's a space-time integral of my equation times, say, minus dv of psi. Use these identities, right? And what's the upshot will be, okay, so here there's an integration by parts that I can do, and I'm going to get, so I'm going to get 1/2, times the integral of on u equals u1 of dv squared. So note that the u equals u1 is this dv points tangentially along this hypersurface, right? This will be a thing. When you do null energy estimates, it's like the regular energy estimate in that you get integrals of squares of derivatives, but the sort of the good terms, well, the hypersurfaces that are involved will be null, and then the derivatives you control will only be the ones which are tangential to them. We saw this in these norms I was writing, was taking into account the structure that was going to appear. All right, so we get this. And then of course you get minus the sort of the initial thing. Okay, then we get all right, so from this one, so right now I'm just writing the boundary terms that come from the integration by parts. So of course, so for example, in reality, so in this double integral, you don't just see, there's a volume form, right? Space-time volume form, which will have, on Minkowski space, will have an r squared. So when I use this integration, but this d by du here, in reality, it's not really a total derivative because there's an r squared times the volume form, right? And so when I integrate by parts, I'll hit that. All right, but right now I'm just writing these boundary terms, and then I'll write something about the other part. Okay, so then here I'm going to get, so then in the d by dv direction, I go the other way. And so here I'm going to get integral of v equals v1, 1/2 of v minus u to the minus 2 times this, and then minus the same thing at v equals v naught. Right. Again, this is consistent with this thing I said about null. So the angular derivatives are tangent to either constant v or constant u, because those are derivatives on the sphere. All right, and then, okay, so that's all the main boundary terms I want. So then we're going to get various space-time terms. One thing that you see is you're going to get some space-time term, and well, if you think about it, because we're assuming again that r equals 0 is, way over here. So don't worry about r equals 0. And since we're away from r equals 0, you don't have to worry about these v minus u to the minus 2. That's like r is not going to 0, so don't worry about it. All right, so basically, if you just think about it, I'm just going to use something very soft. I'm just going to say something very soft, which is now I'm just going to get things that are big O of, I'll write it schematically. This is not meant as a geometric norm. This is just, I just get some space-time expressions that are quadratic in the first derivative, right? Okay, and then I'm also going to get, well, I guess it'll be either 4 minus 4 f. Yeah. All right, makes sense. Okay, so that's nice. I can do the same thing. So we can do the similar thing. Similar thing with multiplying by minus du. I should note, of course, d by dt is basically d by dv plus d by du. So if you add the two, you can add doing the estimate with d by du, and what you get is what would be the dt energy estimate, but sort of evaluated in a null foliation, right? But anyway, sometimes it can be useful to split up the things. All right, so you can do the same thing with d by du, and you get the analogous things, right? So you get the analogous things, meaning that what does analogous mean? So you would get an integral, instead of u equals u1, you would see v equals v1 of d by du squared, right? And then the angular derivative would now be on the other hypersurface. And then a similar space-time. All right, so does this make sense? All right, so this is already in the setting. So I briefly mentioned this Gronwall's inequality, which says basically, well, I won't write it again, but basically, like if you control, at some later time, some quantity, a given quantity at some time in the future by an integral of that same quantity, roughly, then plus some initial data, then in various settings, Gronwall will tell you that you only sort of grow that quantity, in fact, can grow most exponentially. Well, okay, that's a very simple version of it. There's another way that I often prefer to not. Sometimes it's convenient to not necessarily exploit Gronwall directly, but there's sort of an equivalent way in the context of energy estimates to incorporate the sort of conclusion of Gronwall, and that's to include certain weights. And that's something very, again, in this setting, I think hopefully will be not too hard to understand. And then we'll see all this stuff will like immediately just work in the double null gauge. All right, so then we can also incorporate. Well, we can let's say, yeah, we can include weights. We can include weights in here. All right. And again, it's not so what's the upshot? So let's go back. So let's return to the d by dv one. To the d by dv estimate. All right, and now let's multiply. So instead of so now let's multiply by some function. We don't know what we want it to be. Will be by some function a. So by h times dv of psi, say minus, do the minus, where h is a function, say TBD. Okay. And all right, now you can just use all that same structure, right? Then everything, well, okay, let's require first of all that, let's at least want h to be, say, positive. Right. Allow it to be like a weight. Okay, so now you can run through that exact same integration by parts. And well, uh, what's going to happen is that you're going to get you're going to you'll get a term, right? So from this, well, let's look at this first term. So up there, right, we had this term 1/2. So now it's going to be 1/2 of integral S2 du of dv squared, right? So now when I integrate by parts, I'm going to get, so because this h is here, everything is the same. So everything, well, let's just say everything will be multiplied by h, right? But that's not such an interesting change. The key is what's the extra, there's going to be an extra, of course, space-time term you get, because when you integrate by parts, now the derivative could hit this, right? And, extra space-time term. Okay. All right, and so you're going to see, all right, which will be, and one extra space-time term, which will be the following. Minus minus, and then you're going to get minus du of h times. All right, and then there's a similar thing on the, similarly with the angular derivatives, you'll get an extra term. You're going to get, you will get, wait. Yeah, you get the same thing. You get plus minus dv of h times. Right. Okay. And so now, okay, and then of course you also have, like, you can do the same thing with the du one, and similar. Some things permeate around, but then there'll be a du term. Now, what's the point here? Now, the point here is, let's suppose, and this is what we're interested in this problem, but again, all this stuff is much more general than just characteristic initial value problem or whatever, is that you can now say, okay, how can I pick this weight to make things like be nice? And well, so what can you do? What's a natural choice for h? If you want to sort of have some estimate, a close sum estimate that says you control things in the future by various things here. So in the enemy, right, is that there's just all this junk here that we don't know what's going on. And we added this junk, but we can pick whatever h we want. So, and again, it's related to ground wall. So the natural thing is to make h decay exponentially. Right? So, okay, because we have all this junk over here. So we have some bad stuff. Well, it's potentially bad. We don't actually know. Let's say we didn't compute it. Let's just say it like that. So you have big O, so everything got multiplied by h. So there's like this term over here, right? And I'm saying this is the extra term here. So if h is equal to e to the minus au, and well, I can just add that together. Something like this, all right? Where a, well, I want to put minus. Oh, wait. Sorry. We want this to be, no, I guess we do minus. Yeah, sorry, you're right. So then we want, there, yeah, sorry. So I guess I said exponentially going, why exponentially decay. Anyway, exponential. Right, so this h will be positive, right? Okay, but now the point is these derivatives will be back of the form of h, but with a huge constant, right? So now, for example, so du of h, so minus du of h is just going to be a times h, and minus dv of h will be a h, right? So now, if as long as all the, if, especially if this space-time integral is on a compact set, and okay, then all whatever these things, whatever sign they are, these bad terms all have some upper bound. But I just pick this a sufficiently large, then this term that comes with a sort of a good sign or estimate can eat all those things. All right, makes sense. All right, this is a very and you see, so this is like this, so this sort of incorporates the Gronwall estimate because what's the upshot? Because then the upshot is saying it's saying, well, oh, you can prove a great estimate. You can for and also it's immediately clear, right, that this estimate is already like without introducing all the geometry or whatever, it's already clear it's much more general than the wave equation on Minkowski space because I can add arbitrary first order terms. Because all I did to the first order terms was just put absolute value on them, right? And I can eat them with this, control them with this. All right, but it's so what you see then what it says is basically if I multiply my function by something which is decaying exponentially, then I uniformly bound the norm, i.e. the norm grows the most exponentially, which is exactly the conclusion from Grandwall. But this somehow I don't know, somehow I like sometimes I like this is you don't have to go through the Grandwall, you just by hand you make some good terms appear. All right, and this has some more there's also a lot of flexibility here, and this is a very general thing of trying to put in certain weights to make stuff work out. Okay, so that's sort of ingredient number one. Make sense? Okay, then sort of estimate two. Ingredient two, I mean, again, in the context really just of wave equations, it's a little silly, but it will be not completely though. Uh, I mean, silly is, I mean, let's say you can often do things without directly invoking this, but and just to emphasize the analogy with what we later do with the vacuum equations, I want to talk about it. So you can also you can treat the wave equation. Oh, maybe actually there's one more thing worth saying here. So I said this can deal with you add first order terms or whatever. So that in other words, if this f I put over there, that's like all the other stuff. If that includes if that f is things that are linear and derivatives of psi, you're fine. But note that if f is a nonlinear expression and derivatives of psi, then this doesn't tell you anything in and of itself because it doesn't matter how big of a constant you have times dv squared, it's never going to control dv to the fourth, right? Dv upside to the fourth or whatever it could be. Okay, so anyway, so now it's good. So the other thing is you can treat the wave equation as a transport equation for well either d by du or d by dv. All right, so this is of c, of course. All right, so this is a bit silly, but again, so what you can do is you can say, all right, so I'm going to write this now as, so I can just write my equation, for example, as dv of du of c. And then, okay, over here, I'll have, again, for f, and then I'll have something h, I'll put h of c. Or h of c control, this has all the other stuff. So this includes things that are first derivatives of c. So in here are some first derivatives of C, and also this angular Laplacian is there, right? All right, so okay. So because one of the things, again, maybe that's also worth mentioning about this estimate is that this particular type of integration by parts that we do it's one of very important features that at the end, what everything, even before you added in this weight and made to control some extra terms, everything that appears is at the same level of regularity, right? It's all first derivatives. Okay, but you don't have to do that, especially if, for example, in some stage of an argument, you've already done some of these estimates, so you have some things to work with. Then maybe you wanted to prove something like a more refined estimate, using that. And then it's no longer, it doesn't have to be the case that every estimate you do, you know, conserves regularity, right? That would just constrain you needlessly. All right, so for example, you can go here and you can say, all right, so I have some estimates in whatever problem I'm doing, and I want to get some a more refined estimate. So we've already mentioned before. So one option is to just commute your equation with derivatives, prove energy estimates again, and then sort of, for example, to get pointwise estimates, you could do Sobolev or use a Sobolev inequality. We've mentioned that in the past. All right, or one thing you can do is you could say you could integrate this directly. So I could integrate. So I could say du of this at so this is in V. So at some V equals whatever, wherever I want to go, V equals V tilde, right? This will be less than, say, the integral from V equals V naught to V equals V tilde of, I'll just say something like this times uh times your stuff here, whatever this is, times I'll just write it like this. All right, D. So it's like, well, slightly abused notation by saying dV. Okay, and then so you can, of course, you can do that. And then what's useful though is if you want to connect it, and this is what we'll do in many of these things, if you want to connect it back to, again, there's some context where you're proving many different estimates, and you've done, say, some energy estimates. So there are these, so for example, this is not something you can sort of do Gronwall directly to, right? Because you're trying to control du. Well, over here, I mean, okay, there are many reasons you can't, but I mean, there are lots of different first derivatives here. Maybe you do some other transport, but sort of more fundamentally, there's a second angular derivative. So there's just no way you're gonna try to control the first derivative just by second derivative by itself. But you can say, okay, but I know that, let's say at some other stage, I already controlled the integral, like these integrals, whatever. Where are they? I controlled these kind of things already, right? So a very standard thing to do is we can square this. We can square this estimate, do Cauchy-Schwarz, and then integrate over a sphere, right? So so let me just do that all at once. So I can integrate on the sphere, and let me write that now as so I'll just say it's some u v tilde. That this is sitting at u and v tilde, right? So then this after I do, say, a Cauchy-Schwarz. Of course, I also, depending on the situation, I might be interested in exactly what happens when I do Cauchy-Schwarz. Do I get a small constant? Is a large constant? But for now, let's not track that. And I'm going to get, some from V equals V naught to V tilde of integral on F2 of since I wrote the volume forms there. Okay. And so you can get these kind of estimates, right? So the point is, from energy estimates, as long as you've sort of controlled some so from some preliminary energy estimates, you can revisit the equation. You can treat it as a transport equation for, d by du. You can do the same thing for d by dv, obviously, but it'll be in a different direction. And what you get is sort of what naturally a thing that you get are kind of soup. You get a like control of the soup of the integral of those things on spheres. All right, so it's kind of something. So these integrals so L2 norms on the individual spheres. So it's sort of something intermediate between controlling something directly pointwise everywhere and the sort of the natural energy norms. And again, you can of course also, after commutation, so if you suppose you've commuted the equation with 500 derivatives, then you'll have a similar version of this with 500 derivatives. You can apply Sobolev inequalities directly on the sphere too to get estimates. Right? And sometimes this way of approaching it is sometimes useful. And it's particularly useful in the double null formalism. Yeah, as we'll see. Though, I mean, maybe the 2-second version of y. If you remember, so we have these different levels of unknowns with the double nulls. We have the null curvature components, which are curvature. Then we have the Ricci coefficients, i.e. Christoffel symbols. And then there's the metric down below. Forget about the metric. So the point is the Ricci coefficients, lots of them satisfy equations, which are like dv of them or du of them equals something curvature. So it's exactly this kind of estimate that you do, because the curvature, that's the highest level of regularity. So you sort of that at some point is just controlled by curvature at the top level. And then the point is, so if your right hand side is controlled by curvature, it's very natural to get a soup norm integral on a sphere of something which solves a transport equation. This is the analog for just a regular wave equation of that structure. All right, questions? Seems okay. Cool. All right, then maybe we're even ready to proceed. Let me check the chat here. All right, yeah, it's all a little mundane, I guess. Okay, so then some other, let's say, so what are the other ingredients I want to say? Of course, so I've said it in words, but you can commute the equation, right? So for any, well, and since we're working here with the Minkowski box is sort of particularly easy. Again, on more complicated geometries, commuting your thing with derivatives can be very complicated because you don't, Minkowski space has so many symmetries. So there are a million things just commute with the operator. That aspect of it's not too bad. So so you can just so for any, if this just denotes some coordinate derivative, meaning dt, dx, dy, dz, then of course this is just zero. So I can always, and then we can use this notation I've done before, with alpha denotes a multi-index, just which coordinate derivative. So we automatically have this equation, so I can repeat everything. Um, okay, so there's that. And then, yeah, so the final thing is, let me just sort of, I've referred to these Sobolev inequalities that we'll want to use. Let me just state one just for concreteness, and then, and also, again, give a sort of simple-ish implication of one. So, all right, so on the sphere, or in general, if you're working in L2-based Sobolev space, the so-called critical Sobolev exponent will be the dimension of the thing divided by 2, right? But there, Sobolev, of course, is false, right? So you have to go a little higher. Let's, for concreteness, well, let's work just with integer-based Sobolev spaces, okay? So, so therefore, so if f is some function on S2, then our natural Sobolev, the estimate that we'll do is, so this on S2 will be less than, say, F. So we would like to do one derivative, but we can't. So we do, say, H2. Okay. All right, so that's nice. And then so why are Sobolev inequalities important in nonlinear analysis? Well, because let's say you want to do these kind of energy estimates, but then there are things that are multiplied, and that doesn't, you can't take an L2 function times an L2 function. It's not an L2. But the point is that these Sobolev inequalities are related to the fact that if you commute and then in fact work with Sobolev spaces instead of L2, your spaces become algebras, and so it does work. And one very, let me give a sort of, again, just to make sure we're all on the same page, because I don't know about people's hyperbolic PD background. Let's just see one way that can work. So for example, yeah, so let's suppose that n is very, very big, right? I'm going to be very, very wasteful with regularity in what I do. There are lots of reasons to not be wasteful with regularity, but it's just, you can only learn so many things at once. It's good to focus on, it can get distracting if you're really concerned with not wasting derivatives. All right, so we'll be wasteful. Okay, and now suppose we have, you can suppose, so you have some integral on a sphere, and there's some nonlinear term, let's say f times h, and this nonlinear term is, you are taking various derivatives of it, and and you've taken up to n derivatives. Okay. So this is the kind of thing, so again, you're imagining we're applying these estimates and these are coming, this is the f, and well, I mean, there's going to be an analogous thing in reality somehow, well, if f has a quadratic nonlinearity, then these spacetime terms that involve f against something in reality become spacetime terms of three functions. So I'm going to give a version for two functions. In reality, we're going to apply it for three functions often, but whatever. Well, we'll also apply it for two functions, but it's going to be the same. All right, so then the basic point. So all right, so let's suppose you're looking at this. Now the basic point is this thing which is sort of silly, which is just that, okay, this is going to split with the product rule. We don't need the exact formulas for the product. We don't need to track the constants, exactly. We just need to say the following, that this is going to be okay, this is just going to be the sum over n1, plus n2 less than or equal to n, right? Or sorry, I should say it like this, of alpha 1 plus alpha 2 less than or equal to n of f alpha 1, right? So this is clear, right? Just from the product rule. And then, well, at some point, then it's the silly thing, right? If alpha 1 plus alpha 2 is equal to n, one of them has to be less than n over 2, right? So in reality, this is then, I can write this as the sum of alpha 1 less than n over 2, alpha 2 less than n of alpha squared, alpha 2 squared plus the sum alpha 1 less than n and alpha 2 less than n over 2. Right? Nothing fun, no funny business there. Now I'm going to take the one that has the smaller number of derivatives and I'm going to pull it out of the integral in L infinity. Right, so then I can write this. And I'm just gonna write for the one term, you're gonna do the same thing on the other term. All right. So now we can write this as sum alpha 1, not less than, actually less than or equal to n1 over 2, alpha 2 less than or equal to n of the of f alpha 1 L infinity squared times, well, then I can write it like, well, then it's really just h, well, let's go ahead and even write it like, what even? H n, right? And then plus the other term, right? So all I did, I have an integral product of two functions. I can pull out one pointwise norm. Then the remaining thing is now a regular L2 norm. It involves up to n derivatives, so I can do that, right? Okay, now here I can use the Sobolev inequality. And then by the Sobolev inequality, so this is a pointwise L infinity norm of up to n1 over 2 derivatives. So if I'm willing to spend 2 more derivatives, I can control that in L2. All right, so I can put this as h of n1 over 2 plus 2 times hn squared, and then plus the flip. All right. Again, if you are willing to open up an analysis book and work a little harder, you could do a lot more sophisticated things. This is the totally most basic version of this principle. Okay, and so what you see is that so it's not, and there's this, of course, there's a similar thing if you have a product of three functions and you're taking a bunch of derivatives. Again, it's just this principle that if you take enough derivatives, and again, so this is the thing, if you're not trying to really carefully conserve your derivatives. So if you're willing to take a million derivatives, then you'll always have this, the term that you have to control is always like, you can think like basically all the derivatives hit one of the terms, you know? And remember, we also have this high-low decomposition in our norm. This is very much related to that. So the one where all the derivatives hit the thing, that's you're going to have to use the high portion of your norm to control because, well, derivatives hit it. And then this other one, and then all the remaining stuff is going to be way less derivatives. It's going to be basically half, or well, in the triple case, uh, well, whatever, some similar thing. And plus a little offset. But anyway, this is the thing, if these n's are just really big, you don't have to think about it too much. This number is just going to be some fraction of n. So it's going to be way, way, way lower. And you saw, and maybe what's useful to see, what you can see is that from this transport equation structure. So we saw that when we wanted to estimate like the L2 norm of du of c on the sphere, again, that wasted derivatives, quote unquote, because on the right-hand side of that estimate, we have to put in that h term include, say, the Laplacian. But you note that, so we're just controlling one derivative integral in the sphere. Okay, we had to control two derivatives in the energy norm. So that's kind of lost. We would say that estimate, colloquially, people say lost one derivative. All right. Okay. But that's a finite, and if you commute that 500 times, it will still lose one derivative. So in other words, if you control 500 derivatives of the energy flux, then you do that estimate, you'll control 499. Well, maybe, that controls du and dv. So maybe you want to do one more fundamental theorem of calculus to control and get, commute. So maybe it'll be 498. So if you control 500 derivatives in L2 by like doing that process and then integrating one more time, you control 498 derivatives on the sphere. But this thing says, but here, if this is 500, I mean, this is 252, which is much less than 498. Anyway, hopefully it's not that complicated, but somehow it's a really important point. So you can you have a lot of flexibility of what you can do with this guy. All right, so this, and moreover, what you see, if you kind of invoke the Sobolev inequalities just via some inequality like this, you can sort of, it's almost like you don't even, in reality, you can set up your norm, you can sort of always just work with L2 norms on the sphere somehow. And this is the key point where the Sobolev inequality is used, is to control nonlinear expressions, that you can break them up into a nonlinear expression of the norms of the spheres. Okay, so that's, these are the ingredients that will go into the proving the estimate. Make sense? All right, what time is it? Oh, very natural time for a break. All right, so let's reconvene in 10 minutes so I guess 4:09. Give ourselves an extra 8 seconds. Okay, so all right, so now let's start let's do our bootstrap argument. All right, and if I don't finish today, we'll finish on Wednesday. Okay, so if you remember, in reality, we're supposed to prove some estimate in every possible characteristic rectangle, but sort of the way you do it in any given one. So remember, we're in this like region like this, right? And then there's this is like this epsilon that we're going to pick, and then I have to do it in every possible rectangle. The only really relevant thing, and it's not that relevant because it's completely symmetric, is whether in the event that your rectangle has a long side, is along here or along there. But everything is completely symmetric in U and V, so I'm just going to do one. So what I'm going to do is I'm going to focus on this. So this setting. So something like this. Okay. And what I'm going to do is I'm going to call this hypersurface U equals -1. And then we're going to go. So here is going to be, this is where we want to go up to. This is going to be U equals -1 plus epsilon. And epsilon is my small parameter that I get to fine tune later, depending on the size of the data. And then, so here, we can call this V equals 0. And this is V equals V naught. Remember, V naught is not small, but it's something bounded, right? In other words, like the smallness of epsilon is allowed to depend on V naught. All right, and then I have all these high-low norms. So maybe I have to remind us. Okay, so then we have this So let's introduce some name for this norm. I think I called it G epsilon before. All right, so remember, epsilon is a free parameter still. Um, but with all that being said, so okay, and then our equation, remember, was box of psi equals, I don't remember if I did plus or minus, it works the same. Du, something like this. This is just our model equation. It's a good exercise that once we've done this to understand for yourself the natural full range of validity of the argument. In particular, one thing that you should immediately be able to understand is you can add any quadratic combination that involves at least one angular derivative. Is fine. Okay, there's this, and then so our norm had these two pieces, this high piece plus this low piece. Remember, we also had this n, which will denote the total number of derivatives that we're going to take. I'm going to be extremely wasteful here. So no, I'm going to take all sorts of derivatives because I can. They commute. So no, one thing is, like, for example, when I do these Sobolev inequalities on the sphere, I of course only need derivatives on the sphere. But anyway, I'm not even going to keep track of what just because it's for this Minkowski box, it's convenient to use that coordinate derivatives just commute. Right? Of course, well, angular derivatives also commute, but anyway, whatever. All right, and then this high one was, all right, so let's call this thing R. Let me call this R, because I guess I called the whole thing G sub epsilon. So let me call this R sub epsilon. So this will be right. So the high norm, there are two pieces. There's because it's an ingoing piece, outgoing piece. So we'll have the soup over V over from 0 to V naught of the integral of well, maybe V tilde. It's one of these really annoying things when you do this is you end up with running out of like ways to distinguish different V's. There's V0, V check, V hat, but anyway, usually it's okay. So the integral over V tilde of V, V equal V tilde of, yeah, often if you're really writing it out properly, you have to introduce another set of U's and V's, which parameterize your rectangle. So that uses up another set of symbols. Then you really start running out. So along, so V equals constant, go that way, right? And going. So these ones will be, so here we'll control du. Oh, sorry. I forgot my, right, sum over multi-indices less than n of. All right, I won't write the volume form. And then we have the corresponding one in the other direction. So this will be the sum over u tilde in -1 up to -1 plus epsilon of the integral over u equals u tilde of, so now a constant u hypersurface goes that way, and the tangential things there are d by dv and angular alpha plus all right, that's the high norm. And then the low norm, well, in reality, there are a lot of things. You can see that there's a lot of flexibility. I'll just write something kind of lazy. Guess I wrote it all as quadratic quantity. So this one we'll see that I'm not actually, so just to touch back to what the thing that I wrote before, I'm going to write this low norm in terms as an L infinity norm. We'll see that it doesn't really, in some sense, I'm going to keep this philosophy because it's convenient when you work with the double null equations. I'm going to keep this philosophy of sort of really doing things based on L2 norms of the spheres and somehow embedding the use of the Sobolev inequality like this. And so when you do it like this, you sort of don't really need to explicitly put a pointwise norm in here. My low norm could just be soups of integrals on the sphere. I could work instead of a L infinity everywhere, just of the soup of the L2 norm on the sphere. But just anyway, that's a bit of a slightly exotic, but so let's just we don't lose just to connect still to that to more usual formulations of these things. Let's go here. Let's say again, remember there's tremendous you have tremendous flexibility in what I can do here because I'm not being careful with n. So I'm just going to say less than n over 2, and then I'm just going to put infinity of the whole thing. Okay. Okay, so now we want to prove this, and now what I can assume from the beginning. So, all right. So now, we're going to assume that g epsilon is less than some, say, 2p, and need to show that this is less than p, right? Where we can, where p will depend on the data. Right? So this looks a little weird because first of all, you might have noticed in millions and millions of inequalities I write, I'm always writing less than with the little twiddle thing right under it, meaning there are all these implied constants everywhere, and I have not displayed any predilection for tracking those constants. So you might wonder, how could I ever track the difference of 2 times p and p? Well, that's because, well, it's true, this is what you need to show in some minimal. This is not sort of how, well, it's not how this argument's actually, we're going to prove something sort of a lot easier to track. Right. So what we're actually going to do is the following. So I wanted to introduce, so let's introduce constant d. D. This is going to stand for it. This will sound maybe okay. The expense of being possibly a little informal for now, but it'll become clear. We'll let d, the constant d, which will be a suitable Sobolev norm of the data. All right. So there'll just be all sorts of, every time we do estimates, they're just going to be, like with these energy estimates or this transport equation. Oh, I didn't write the initial data for that transport equation estimate. No one stopped me. Right. I integrated it from v to v tilde, but there's of course an initial term of v equals v0. Just I did the fundamental theory of calculus. Anyway. Right. Just so, for completeness. Okay. Anyway, so when you do all these, which is just to say, when you do all these estimates, there's always some term coming from the data, right? And basically, after I do all of those, I'm going to just sum all of those things, and maybe to be careful, multiply by 500, and that thing is d. All right. So d will be defined in the course of the proof by just whatever stuff shows up. Okay. And so this is what you actually will show. So what we actually will show. So we will actually show something like this. We will show is that we will control this will be less than some constant, some implied constant, times things just explicitly which come from data, explicitly only depend on data. Yeah, some suitable, let's even say power of, I'm not saying this even scale. This might be like some norm to the 100th power or something, whatever. It's just some stuff which is computable at some point by data. So we're going to show this plus, then there's going to be some, well, again, it might be, depending if we're lazy, some q, say between 0, well, some q greater than 0, there's going to be some epsilon to the q. I don't remember exactly. Maybe might be just epsilon. I forgot. All right, times some times some function of p. So for some. Okay. Or I should say times some function of, it's more like this. All right. This is kind of actually what you do. All right. So you're going to prove estimates, and what's going to happen is you're going to either somehow just explicitly when you estimate the term, it's only going to involve the data. And then that's kind of, well, okay, we'll get to the conclusion, but okay, it'll either just involve the data. Like you don't invoke the bootstrap hypothesis doesn't naturally show up as something on the right-hand side of your estimate. Or you will invoke the bootstrap hypothesis and there'll be maybe some complicated way. So you have some function of this norm. So what I mean, invoking the bootstrap hypothesis is the fact that this thing is finite. Okay, but it's going to come along with some small parameter. All right. And because you can pick, whatever P is, you can pick epsilon very, very small. So P depends just on the data. So whatever D is, it allows you to, P will be like some bounded by something depending on D. And then epsilon can be smaller than all of that stuff. And so you can effectively, so this thing will effectively, you can make this as small as you want. This will be less than D. So under the bootstrap assumption, and then picking epsilon small enough, this will all be less than D. And then because D is much smaller than P, this in particular, because you can pick P to be bigger than D, you can pick this so that this is true. And so this is, I mean, does it make sense? Yeah. And so the point is, we still don't have to track constants carefully. So there's never an issue of tracking some 2 through the whole argument and making sure the 2 gets a 1/2 somewhere. That's not, I mean, you can do bootstrap arguments like that, but that's not how this will be something you won't need to go to that granular level of detail. There's just a dichotomy. It's either you're going to, any term, either you just explicitly show that you control it by the data, or when you invoke the bootstrap hypothesis to control some term. Again, remember, you can think of that as like some kind of continuous in time induction. So you say, oh, well, this thing's only like 2p, then there's always going to be an epsilon floating around, and epsilon will be really small, so that somehow it has to work.
Just something that's small and only depends on.
It's not small, not necessarily small. D is remember, data is allowed to be anything, but whatever it is, it's like how V naught is not small, but it's just something. The data is something. It's finite in this norm. In fact, we could assume it's smooth. That's fine. And this is something which will, like I said, in the course of the proof, we'll see exactly what it is, but it's going to be just ultimately controllable by some power of a Sobolev norm of the data. And that might be large, but it's fixed because we've worked with a given set of data. And then given that thing, we run this bootstrap argument with a P which is sufficiently big depending on that. That was part of that argument that I did last time, that you needed to allow this P to be big, but only depending on data was enough. So this P you have to work, you can only use this bootstrap assumption with a sufficiently big P, but only depending on the data. And then I'm going to take epsilon small though, depending on the P. And then I need to verify that my thing, I could assume 2P and I need to verify this, but what I'm actually going to do is prove this, which will at least sort of, and from here, it's easy to get to here. Even though, like I said, if you're not familiar with this, it looks very weird. It looks very weird how you could possibly go from this to this because you have to track constants, but you don't. All right, makes sense? Okay, so
This integration, we look at G epsilon or R epsilon. Because I think last week you said we could reduce it down.
I called this thing RG. I mean, I don't know. I mean, I could rename this. I was just using the same name, but then
So the actual vector, not the D shape.
yeah, I don't know. I called the norm. This is just because I'd use this definition for the norm, but the region. I'm applying the norm. Yeah, I don't know. Maybe I should recall this R epsilon. Anyway, that doesn't matter. I mean, we're not going to actually like invoke this notation because I'm just going to write P's whenever I use the bootstrap. Okay, but yeah, I mean, you're right. Maybe that's a little confusing. Maybe just to emphasize, yeah, everything is all localized on R epsilon. Everywhere here would be R. All right, any other questions? Okay, so then let's start. Uh, Pretty standard. Yeah. Well, more than just wave equation. Any It's standard for nonlinear, normal nonlinear PD are often broken up like this. And I'm just presenting the most simplistic version thereof.
The SDE, I was in the video, I see the SDE repeat here, but it doesn't seem like it's playing in very much. It was like a side discussion.
It was the previous, I think there was a talk here. No, there are no stochastic differential equations here. I'm not. It's already hard enough to do this in a deterministic sense. Well, sometimes the random things get easier, actually. But anyway, let's not get into that. All right, so what do we want to do first? Well, I'm looking at my notes as if I have it planned out very well. Okay, so let's start. We're going to start with estimating some low norms in terms of well, like I said, in reality, I'm not going to work. I wrote this low norm because it's kind of the standard way that the low norm is most conveniently phrased in terms of a pointwise thing. In reality, I'm going to work with the fundamental low, the true low norm that I'm going to work with is this L2 on the sphere. Right, so I'm going to prove an estimate now for these L2 norms on the sphere. Okay, so let's look. So here's so let's write our equation in the following way. So dv of psi equals, and then I'm going to write it as there's something which is big O of well, then I'll just say I can write my equation as du dv of psi plus something which is big O of du of psi plus yeah. Do I want to say this? Or do I want to start? Well, okay, yeah, in general, we can write like this. Plus du d psi plus dv plus dv of psi plus these angular derivatives, right? Here's my derivative loss term, and then I have my nonlinearity. Okay. Moreover, I can commute this equation with coordinate derivatives, right? So for every, what I have is, right? So for every alpha, and so we're going to stick, so our total number, what's our thing here? So remember in our high norm, we eventually control n derivatives in L2 and then one angular derivative. So that is the total. So if I'm going to, so the total number of derivatives I can see, well, let's focus on this angular one. I can control n plus one derivatives in L2. So if the maximum amount that I could possibly commute this with to be reasonable would be to commute with n minus one, right? So if alpha is less than n minus one, then du dv of psi of this, right, will be less than, well, I already used alpha now, will be less than the sum of beta, well, less than n minus one of, well, applied to all this. Let me not rewrite it. Okay, so now I can do this, now I'm going to use this style of equation. All right, and so what's going to happen? So and I'm going to try to control. I'm going to be interested in controlling the this d by dv, this d by dv norm. All right, so I can control. So I have d by dv here. Right, so this will be less than the integral of the sum of beta. So this is at, so let's say this is at some, let's say some u tilde v tilde. This will be less than the integral from, I integrate from minus one up to u tilde of all this stuff with You see these things get to be really a bit of a notational headache. That well, in here I'll write all right. Okay, and now I'm going to, I can also square, right? I can square. All right, all my constants, I don't care. They can depend on n. I'm not gonna worry about that too much. All right, and now I want to apply Cauchy-Schwarz. So here's where I made this comment that there I just applied Cauchy-Schwarz and didn't write too much. Oh, and I forgot the data again. But this is what's nice. We just write plus d. Remember, d is just something. I'm not even, like, just emphasize, I'm not even tracking the like scaling of d, whether it's really something quadratic in the data. I mean, it's just d. Okay.
C here is exactly the key that you talked about.
Yeah, interpreted in this. It stands for anything that's coming from data. Like I said, like I'm just saying, because I would write this with d, and then when I square it, I don't want to write d squared. I'm just going to write d, is what I'm saying. That just could be confusing, is why I say that multiple times. All right, so now I'm going to apply Cauchy-Schwarz. Then there was this point I made up here that when you do Cauchy, you can always do Cauchy-Schwarz, but you might want to, depending on the size of the region, pay attention to the constant you get. And here's where we want to pay attention to the constant. So when we do Cauchy-Schwarz, what's going to happen? Well, I'm going to pick up, the point is u tilde, whatever it is between -1 plus epsilon and -1. So the region of this integration is size epsilon, right? So when I do this Cauchy-Schwarz, I'm going to pick up, I'm going to pick up the integral from -1 to u tilde, which is less than epsilon, right? So I'm going to get, and this is going to be the first example of, we're going to see this paradigm in practice, and I think it'll then be clear exactly how the bootstrap assumptions are used and stuff. All right, so then what we're going to get is epsilon, right, times integral from -1, oh, stupid sum, epsilon times the sum, all right, times this integral of du of this. Oh, well, my d is in the way. Let's see. All right, get this plus dv of this. Like I said, these are all, the subject is the notational nightmare. All right, but I'm doing all of this more carefully so that when we do the Einstein equations, I don't, right? Because then you'll understand everything perfectly, and then we can just hand wave there. All right, plus d. All right, and so this is exactly a kind of, so like I said, this is a good place to illustrate this, how this works in practice. So the point is that because this region is small that I'm integrating in that direction is small, this epsilon will be very small. So all the terms coming here, I can, I'm free, if they come controlled by the bootstrap assumption, in other words, if they show up at all in that, what we now call our epsilon norm, then they are just totally fine. Because again, epsilon is going to be much, much smaller than the p that shows up in my bootstrap. And in fact, yeah, anyway, so epsilon will be much, much smaller than p. All right, so now we just have to look which things show up. And the point is, well, basically, well, not this one, right? So remember, so this is an integral in the, wait. Yeah. So what shows, so this is an integral in the in the ingoing direction. So I control, so the natural fluxes that would be controlled are all the ones tangential to that. So let me put, so this is something that appears in my energy norm, right? And this is something that appears because I was careful not to commute too much. And then, okay, we'll have to think about this one. All right. This one doesn't appear, but I also, if you think about it, I can control it by exactly what I'm estimating. Okay, but let's go one step at a time because this is the first term. We'll speed up eventually. All right, so I'm putting check marks on terms that, that after I integrate over the sphere, I'll be able to control. So now so we did that. So now let's integrate over the sphere. and invoke the bootstrap assumption. And I'll also introduce a convention that, again, is very standard, at least when these kind of these situations are discussed informally. So before I write that, so let's introduce our convention that I don't have to say it explicitly, but every time, so anytime something of the form epsilon to the q, some function of this and R epsilon shows up, whenever that happens, I pick epsilon, I immediately choose epsilon small enough. I missed some terms. Some small enough so that this is less than D. All right. Okay. All right. So in other words, okay. So from this observation that these are terms that show up in the fluxes, and because I took enough derivatives so that it didn't mess up, I immediately conclude that after integrating over the sphere, so I get that the integral over S2 at u tilde v tilde of dv of c of alpha is less than, so I get, well, I'm just going to write the things that haven't been controlled yet. So I have this epsilon, I have this beta is up to n minus 1 of integral here of, so they're the, and then I have plus the nonlinear term. I'm waiting to do my product rule. We're going to quickly use that thing I said about the splitting up the derivatives of things on the spheres in a second. All right, so we have these terms that aren't controlled, and then I can just immediately write D, right? So you see, that's sort of how that works. Okay. Okay, and now we have this term, but okay, so now let's, oh wait, I wrote the wrong one. Sorry, right? Because this dv only shows up in this is an integral. This is like, I've been doing the subject for this many years, and I still get confused. And when I write a u there, I should think it should be a u. Anyway,
We get rid of, like, I know that those ones are good because we have control over them, but so then they get absorbed into D. When you
I use this convention.
Oh, okay.
So to go even slightly, just to write again, so that we're really on the same page. So once I integrate the spheres, these are now less than epsilon. So if you wanted to write it all completely, it would be times epsilon, and then you would write these integrals on spheres are controlled by psi r epsilon squared. My convention is that anytime I see something like this, I immediately choose epsilon small enough so that it's less than D. Because there are always going to be D's floating around, so there's no point in doing better than D. I mean, in fact, I could choose it small enough that it was 100, 1 over 100 times D. I can make it smaller than anything because I'm allowed to do anything I want with epsilon. But D is already won't, or once it's less than D, it doesn't improve my results because there's always stuff depending on D. Make sense? All right. Okay. So then we have these terms. Okay. So now let's look at these one by one. This term, does anyone have a recommendation? So I already said, I mean, the point is that it's sort of the same thing I'm estimating on the other side, right? I mean, that is to say, I can just absorb. I mean, if I take, because I'm doing this for each u tilde, right, in this range, this is just an integral over that same range. If I just put a soup here over all u tilde between -1 and whatever, then I can control, like, well, just this term at least. Well, we're going to do a similar thing over here, but we'll get to that. I can control this term just by that same thing that I'm controlling over there, and then times things that involve small ranges of integration. Well, I already have an epsilon. I don't even need to use that anymore. But in fact, will be epsilon squared. So if controlling something by that same thing times epsilon squared, I'll be able to absorb it. Right. So let's do that step. All right. So now I'm gonna just write soup over u tilde and -1 up to -1 plus epsilon of oh, and then I should sum. I guess I should sum over all these. I mean, this is a sum over all the betas, right? But this was one particular alpha, but so now let me do the soup and sum over all the ones that I get. So I do the soup and then I do, so now I'm summing over all of my alphas, right? I picked, because I did this thing for any alpha n -1, so I can do it, I can just sum over all of them. Of course, the constants depend on n whenever I do this, but I don't care. N is just something sufficiently big, right? In fact, like even with my sloppy use of n, even like n equals 8 would be enough, something like that. It's not like 5 million in reality. Okay. So I'm gonna have this, right, is less than, well, so then this quantity, so this part of it, I'm just going to pull out the soup, and then this integration is size epsilon. So I'm gonna get less than epsilon squared, and then I don't know, let's just call this thing q. I'm just gonna get epsilon squared times q, right? Plus, right, there'll still be this term to deal with, epsilon times times right. Okay. Um, but that just means I can write q is less than this, right? Because epsilon is small. Does this make sense? Okay. All right. And now I come to this term. And basically, I want to basically argue like this in some sense, because you can see over here that this term I'm estimating, is here. And there's an epsilon. And somehow the u derivative, for example, I could control with some bootstrap thing. All right, but I have this problem that this sort of by itself is, well, this is an L4 expression, but that's exactly what all of this nonsense is designed to help us with, right? So, so now using the above board, right? I have, well, maybe, oh, but I don't want to erase it because I'm going to use it. It's bad. Let's go over here. Um, yeah. So I'm going to get soup over u tilde -1 to -1 plus epsilon of the sum of alpha plus n-1 of the integral of this over u tilde b tilde of d dv of this, all right, is less than what? Well, now what this says is that basically, so this is exactly a, at most hn-1. So this part here is at most like a du of psi times dv of psi and hn-1 squared of S2. And what this principle tells us is that, well, first of all, we know it's an algebra because n is large enough, but more than that, I can split it up, and I can split it up in a way that the sort of, number of derivatives is nice. which in fact, I don't even know that I need that, but let's write it anyway. Okay, so I get epsilon and yeah, so let's write it now. So we have integral from -1 to u tilde, and then I sort of get well, I'll write it as two terms here. So we'll write it as, so one possibility is du of psi in h n, it's n minus 1 over 2 plus 2 squared times this. So you see why I tried to delay doing actual estimates for as long as possible. It's not very fun. Times du. These are all in spheres, right? Spheres. And these are, it's the end, the sphere, each u, the view is fixed, and I'm integrating u, and it's each of the spheres that you get, right? Times hn squared. No, this is -1. This is -1. H n minus 1 over 2 plus 2. Okay. Right? All right. Now, of course, this expression here just controls exactly dv of phi and h n minus 1 squared, right? Soup over, again, these are on all these u tilde. Okay. All right, and so now it's exactly, well, basically it's just the same game. So now the point is, because I've split these things up, I can do basically, I can treat it like I did over here. So I can pull out, so you see, so look at this dv here is n minus 1. This is where so here I didn't actually need to use this. I could have used just set it with an algebra. So over here you see n minus 1 here. So even though that's the high regularity term here, and I actually control that on this other side. So I don't need to exploit that the relative size of these numbers actually. So I can pull this out. I can take the soup in the range of integration. I can pull this out in infinity to take this outside, put the soup in u tilde, right? And then I can also do, the same. This is just controlled in here, so I can do the same thing. So I can say this. Oh, of course, the ever-present and important plus d. It's like the plus c in high school calculus that you lose a point if you forget. All right, so now I'm going to pull out just things that I'm going to control by the same norm. I'll pull it all the way out here. So I can write soup of u tilde and -1 to -1 plus epsilon of dv squared hn minus 1 of s squared. All right. And then what remains, again, I should either do the worst case scenario is this one. And so times epsilon times this yeah, times that. Like I'll just write it like this. Plus, right? All right, so all I did, so you see, I just pulled out these are integrals in u, and I did a soup in u and pulled them out, all right? But the point is that this is just this thing, right? So as long as I know that this thing is sufficiently small, I can absorb the right-hand side into the left-hand side. And again, because I have an epsilon floating around, I'm not afraid to use my bootstrap hypothesis, all right? With the slight caveat that I can't quite just use this convention. In other words, I don't want to just say that this is less than d, because then I don't have smallness. So maybe what I want to do is say like epsilon to the 1/2. So of course you can do whatever you want with epsilon. So that's sort of, all right. So then I say this by my convention, because this is, remember, I haven't taken, I ultimately control in this is of course, I square and integrate on the spheres. This is just an integral on in U on the sphere. This is the kind of thing you get in the null energy that's in my norm. This is in the high norm, right? Because I didn't take too many derivatives. In fact, I have another space. I could have taken one more because the angular one already stopped me from here. So this is something which is controlled by the norm, but my convention, I have an epsilon that's small, so that's d. So then I have now this epsilon, as long as it's less than, d squared over 500 or whatever. Well, there's some implied constant here, whatever. D squared divided by something big enough to kill that implied constant, I can absorb it here. And so the upshot is dv squared hn minus 1 of this is less than d. All right. And so we've succeeded in controlling any term that involves at least one dv derivative up to n minus 1 derivatives of that and L2 on the sphere just by data. You see, so this inequality does not reference the bootstrap assumption. Right? Okay, so this is the idea of how these arguments work. It's a natural time to ask for questions. I'm sure I made a mistake somewhere in it's so easy to make typos. Yeah.
Again, this apartment, go from the first inequality to the second one later.
Which one?
So first inequality,
Here?
yeah, go down.
Yeah, so I'm just saying this is some thing, call this h of u.
Yeah.
And this thing is integral of this of h of u du. And all I did was said this is less than the sup over u. And well, I just did the full range of integration, because this u tilde is less than minus 1 plus epsilon. So I can do this, the sup of this times just this and then this integral, I can just do the maximum size that it could be. Well, and there was already an epsilon outside, right? So I had this. And then this thing is epsilon. I don't need that extra epsilon, but yeah.
So the amounts that you're deriving are pretty tight then, and besides this, some low constant that you're just kind of.
What aspect of it is tight?
Like, so you use Cauchy squared, so I guess it's likely to. I mean, and most of the derivation seems to be just Cauchy squared and then kind of breaking things into pieces. So I don't see anything where a lot of symmetry would be appropriate. I think where
Symmetry broken. I mean, yeah, it's probably these things, it's likely some of these things are sharp. I mean, this term is not the kind of the thing where right now, I mean, this estimating these things. So basically what I'm doing is, this is like the short direction, right? What I'm doing is I'm going this way. I'm using that I just assume something here and then I'm going here. And this is where I have the small parameter. So it's kind of like, that's not where things go wrong. And we had this example of where this theorem is false, when you have the bad nonlinearity. And like if you had du squared, duc squared, and sort of in a way, it's not, even though here I already used, I mean, I of course have used the special structure, right? Well, the way I phrased it, yeah, you actually probably, I mean, the way I did this estimate, I use a special structure, but this is not actually the part that's most dangerous. So we saw that that other, when you had, instead of du dv, when you had du of psi squared, well, I guess that was relevant for that way. So let's suppose the relevant one going this way, the enemy would be no, it would be still du. Yeah. So because remember, then you would have this, if insofar as the wave equation is like dv of du, and then if you have like du of psi squared with the wrong sign, it might blow up, right? That was, I did like 90% of the proof that could happen. You see the danger is when you integrate this way. And so it's there that it's sort of more interesting to think about to what extent the estimates are sharp. Yeah. But here it's kind of like, I mean, there's still things to work out. I mean, if it's your first time looking at it, there's a lot going on, but somehow this is not the worrisome direction. And of course, all of this is all contingent on the bootstrap eventually holding. It's one of these, it's either all wrong or all correct. So it's also like to say some partial part of it is sharp is also a little, that this works is contingent on the dangerous part working because I controlled some terms assuming that. All right, other questions? All right, so we're almost out of time. Yes. Oh, there's one on Zoom. Cool. Do we always need to assume small data to run the bootstrap argument? Not only do we not always need to assume it, we're not assuming it. So this is an example of not assuming small data. I remember the smallness in the problem comes from epsilon, but this constant d is not assumed to be small. Does that make sense? Person on Zoom. It's weird that their things, oh, because they didn't adjust because of daylight, because their timestamp was 4:53. It was confusing to me. But spring forward. Okay, so well, we're basically running out of time, but let's so the next step is going to be to do is to do well, okay, well, actually no. Let me in the last few minutes what I can say is the following. So we can go, let's go a little, there's some more things we can quickly extract from this. So we did sort of hard work to control this norm. Okay, so first of all, I control this. I can immediately use the fundamental theorem of calculus. And I can use this to control, in fact, I can control this. So by fundamental theorem of calculus, just integrating in the v direction on the spheres, I can just get this. All right. So am I right? Because when I integrate in the v direction, I pick up some term from down here, right? That's just data. And then, so all I'm saying is that I can control this by some integral, in v of, dv of the solution, right? And then, okay, then I integrate over the spheres and do Cauchy-Schwarz, whatever. All the regions are bounded. So I also get this. And so in particular, I can do Sobolev inequality, right? And now I get that, so by my Sobolev inequality, if I lose two derivatives, I also get, so I can control up to this n minus 3 in infinity, right? Well, yeah, just on the whole space. Well, let me write it just like this. In particular, I control up to n minus 3 derivatives squared by data. Okay, so which in particular covers that sort of psi low, right? All right. But of course, like I said, it covers it, but it covers it, of course, conditional on the other thing closing at some point. So it's not that we're half, it's not a whatever, half a proof is not a proof. Right? Okay, so we'll finish. So on Wednesday, we'll do oh wait, oh, is that clock wrong? So it's 5. Okay, I didn't even realize that before. Oh, the Zoom was correct and that was wrong. All right, so yeah, so on Wednesday, so what we'll do is we'll complete this argument by proving these by, all these L2 bounds that we use in a fundamental way here. We're going to have to prove those. Again, we can use the bootstrap hypothesis, but we can only, again, you can only sort of use the bootstrap hypothesis fully when there's an epsilon coming along for the ride. And, just the 2-second version is again that we're going to get, so one, yeah, we'll see. So there are two things that will go in there. So first of all, when we do the energy estimates, the errors will be like space-time terms, right? And so they're going to be all the nonlinear things that we have to control. Those are the scariest ones. The nonlinear ones are going to be estimates in this rectangle. This rectangle has this like just this part which is small, right? So if the terms that show up there, if you sort of control them in this direction, then you have an integral over a small direction of something that is in your bootstrap norm and you're good. Kind of like, I mean, we use something like that here, right? So that's kind of derivatives that are there. So kind of things that are like dv or angular, because they're integrals in this direction, you can use the smallness in the other way. The scary term is that you're afraid of is the d by du term, because that one, it doesn't show up in that flux. It only shows up in this flux. And so you can't kind of, and unlike, and here also, because it's really an L infinity L1 estimate that I squared. I could do Cauchy-Schwarz. I could go in the passage from L1 to L2, I gain something. Here, this is just like, is really an L2 estimate. So I get this thing in L2 here, and I don't, I have no trick to get smallness. So this is kind of the thing you're afraid of, is seeing like d by du. And of course, we know the theorem's false, because if you have just a du term by itself, the theorem's false. So it's a good reason to be afraid of it. But the thing that will save us is that when the du shows up, it's multiplied by dv. And you can use that somehow, that you already have some good estimate for dv effectively. And you can use that you have the dv structure to kind of say, well, it's du times dv. Because dv is good, this is not really a nonlinear term. It's really like a linear term. And somehow then you say, okay, in the worst case scenario for a linear equation is that I grow exponentially. And so we'll be able to use one of those exponential weights to deal with that term. Anyway, we'll do that next time. Okay, so I'll see everyone later.